Have you ever looked up at the moon and wondered what secrets it holds? That glowing companion in the night sky isn't just beautiful, it's a time capsule, a mystery, and a guide all at once. From shaping life on Earth to inspiring myths, art, and exploration, the moon has influenced humanity in ways we barely notice. Today, we're about to uncover 100 fascinating facts that reveal just how extraordinary our closest celestial neighbour really is. Fact 1. The moon's age, roughly 4.5 billion years. Have you ever looked up at the moon and wondered just how old it is? Well, the moon isn't some new neighbour in the night sky, it's ancient, almost as old as Earth itself. Scientists estimate it formed around 4.5 billion years ago. To put that into perspective, if Earth's history were a 24-hour day, the moon popped into existence just minutes after the very first signs of our planet appeared. The way we know this is pretty fascinating. Scientists have studied moon rocks brought back by the Apollo missions. By examining radioactive isotopes inside those rocks, they can measure how long atoms have been decaying, a cosmic clock of sorts, and it turns out the moon is practically a fossil of the early solar system. What's incredible is that the moon was formed when Earth was still a young, fiery planet, bombarded by asteroids and meteorites. The moon has seen it all: giant impacts, volcanic activity, and billions of years of quiet orbiting our planet. That's why it still carries marks from those earliest moments, like craters and old lava plains we call Maria. Thinking about it this way, the moon is like a time capsule. While Earth's surface changes constantly, erasing its earliest history, the moon preserves a record of what the inner solar system was like when planets were still forming. So, when you stare at the moon tonight, you're actually looking at something almost as old as time itself, a silent witness to the birth of our world. Fact 2. The giant impact hypothesis. Here's a story that sounds like something out of a sci-fi movie. Billions of years ago, a Mars-sized object, scientists call it Theia, slammed into the young Earth. The collision was catastrophic, throwing enormous amounts of debris into space. Somehow, all that debris eventually clumped together to form our moon. This is the essence of the giant impact hypothesis, which is the leading explanation for how the moon came to be. It's a wild idea, but there's evidence to back it up. For instance, the moon's composition is strikingly similar to Earth's outer layers, which fits the idea that it was born from Earth's material. And computer simulations show that a massive collision like this could easily fling enough debris into orbit to create a moon-sized body. The impact itself would have been unimaginably violent, melting parts of Earth and sending molten rock into orbit. It probably took millions of years for the debris to settle and coalesce into the moon we know today. The idea that something so calm-looking in the night sky was born from such chaos is mind-blowing. Interestingly, this event might also explain why the moon has a relatively small iron core compared to Earth. It didn't form from the entire planet, just from the outer layers that were blasted off. So every time we look at the moon, we're glimpsing the aftermath of one of the most dramatic events in our planet's history. Fact 3. The moon's composition, similarities with Earth. You might think the moon is just a giant rock floating in space, but it's actually made of stuff surprisingly similar to Earth. When scientists examined lunar rocks from Apollo missions, they noticed a strong resemblance to Earth's crust and mantle. In other words, the moon is basically a close cousin of our planet in terms of what it's made of. Both Earth and moon are mostly made of silicate minerals, basically rocky stuff rich in oxygen, silicon, magnesium, and iron. But here's a twist. The moon has much less iron in its core. That's one of the reasons it doesn't have a magnetic field like Earth. This fits perfectly with the giant impact hypothesis, because it suggests the moon formed from Earth's outer layers, not the whole planet. Another cool fact is that isotopes of oxygen in moon rocks are almost identical to those on Earth. Isotopes are like atomic fingerprints, and this matching tells us the moon and Earth shared a common origin. Scientists even use this clue to argue that the moon didn't form somewhere else and get captured. It literally came from Earth's material. Knowing that the moon is made of similar material also explains some of its behaviour. For instance, it has volcanic activity in the past, but the lack of iron and water prevented it from forming a thick atmosphere, or sustaining long-term tectonics like Earth. So, in a way, the moon is like Earth's quiet sibling, sharing the same DNA, but living a calmer, slower life in the sky. Fact 4. Lunar magma, ocean. Theory. Right after the moon formed, it wasn't the grey, cratered rock we see today. Scientists believe it was covered in a vast molten sea called a magma ocean. Imagine the entire surface glowing, bubbling, and flowing. Pretty different from the calm moon we know. This magma ocean formed because the moon was extremely hot from the energy of its birth. The giant impact hypothesis explains that the debris clumping together would have produced enormous heat. Over time, heavier minerals sank toward the moon's core while lighter minerals floated to the top, forming the crust we see today. Evidence for this comes from lunar rocks, which show signs of slow cooling and crystallization. Certain minerals, like anorthosite, are lighter and rose to the surface, creating the bright highlands. Darker rocks in the Maria sank, filling in basins. This process basically froze the moon's first landscape in place. Thinking about it, the moon started as this chaotic, glowing world before slowly cooling into the serene satellite we're used to. It's like a story of transformation, from fire and chaos to quiet stability, happening over billions of years, and every crater, ridge, or mountain we see is built upon the foundation laid by that ancient molten ocean. Fact 5. Formation of the moon's crust. Once the moon's magma ocean began to cool, it didn't just harden randomly. Heavier materials sank, lighter ones floated, and the moon's crust slowly formed. The outer layer we see today, the bright highlands, mostly comes from this process. These highlands are rich in a rock called anorthosite, which is lighter and reflects sunlight, giving the moon those beautiful silvery tones we see. Beneath the crust, denser rocks like basalt eventually form the Maria, the darker plains that fill huge basins. It's fascinating how the moon's appearance is literally a map of its earliest geological processes. Even though the crust is solid today, it wasn't always that way. It took millions of years to stabilize, and the crust's thickness varies. The far side of the moon has a much thicker crust than the near side, which is one reason the far side looks so different. This difference is connected to the moon's formation story and early molten ocean. The crust's development also affected volcanic activity. Lighter crust allowed magma to seep through weaker spots, forming lava plains that later cooled into the Maria. Every crater, ridge, and basin is built on top of that ancient crust, telling a story that goes back 4.5 billion years. Fact 6. Early lunar atmosphere. A fleeting presence. When most of us think of the moon, we imagine a barren, airless world, and that's true today, but it wasn't always completely devoid of atmosphere. In the earliest moments after its formation, the moon may have had a very thin, temporary atmosphere. Scientists believe this early atmosphere formed from gases released during volcanic activity and the cooling of the magma ocean. Imagine the moon glowing hot after the giant impact, spewing volcanic gases like water vapor, carbon dioxide, and sulfur. For a brief period, these gases would have surrounded the moon in a thin, ghostly layer. But thin is an understatement. It wouldn't have felt like the breathable air we enjoy on Earth. It was probably more like a faint whisper of gas, just enough to slightly affect the surface environment. This early atmosphere didn't last long. The moon's weak gravity couldn't hold on to the gases, and they gradually escaped into space. Solar wind, streams of charged particles from the sun, would have stripped away most of it. Still, the brief presence of this atmosphere could have influenced the moon's surface chemistry and helped form some of the minerals we find in lunar rocks today. It's kind of poetic. The moon once had this ghostly breath, a fleeting reminder that even barren worlds go through dramatic changes. And this early atmosphere connects to other facts like the moon's slow cooling and the formation of its crust, showing how all these processes work together to create the moon we see today. Fact 7. Differences between near and far sides. Have you ever wondered why the moon always shows the same face to Earth? That's the near side. But the far side, what we rarely see, looks completely different, like a whole other world. One of the biggest differences is that the far side has far fewer Maria, those dark lava plains, and more rugged highlands. The reason lies in the moon's formation and early history. After the magma ocean cooled, the crust on the far side ended up thicker than the near side. This made it harder for volcanic lava to break through and form Maria, while the near side could more easily develop those smooth plains. Another difference is gravitational. The Earth's gravity actually influenced the Moon's crust as it solidified, pulling material and creating subtle variations. Over billions of years, meteorite impacts have also left their mark, but the far side remains more heavily cratered and jagged. It's fascinating to think that the Moon we see isn't representative of the whole satellite. The near side is like the curated, friendly face we always admire, while the far side hides its chaotic, rugged story from our eyes. And when we explore further, like with lunar orbiters, we uncover the full tale, linking back to the Moon's molten beginnings and early crust formation. Fact 8. Moon's slow cooling process. After its fiery birth and molten beginnings, the Moon didn't instantly become the cold grey rock we know today. Its cooling process took hundreds of millions of years, gradually solidifying its crust and forming the surface features we see. The slow cooling was influenced by several factors. The Moon is relatively small compared to Earth, so it lost heat faster than our planet. But early volcanic activity and internal heat from radioactive decay kept the interior partially molten for a long time. This allowed the crust to shift, magma to flow, and the highlands and maria to take shape. Even today, the Moon isn't entirely dead. There are tiny moonquakes caused by residual cooling and shifts in the crust. These small tremors are echoes of the Moon's long thermal history. When you think about it, every crater and ridge on the surface is layered on top of that long, slow transformation from fiery molten rock to a silent celestial companion. Fact 9. Lunar water, evidence in ancient rocks. For a long time, scientists thought the Moon was completely dry. No water, no ice, just dust and rock. But then came a surprising discovery. Tiny traces of water in ancient lunar rocks. Apollo mission samples revealed hydroxyl molecules trapped in minerals, showing that water existed during the Moon's early history. Some of this water likely came from the volcanic activity in the magma ocean, while other portions could have been delivered by comets and asteroids. The idea that even the Moon, a seemingly barren place, had water billions of years ago is fascinating. It also connects to later discoveries of ice at the poles, hinting that the Moon's story is far more complex than we once imagined. Water on the Moon has huge implications. Not only does it help us understand its formation and evolution, but it could also be a vital resource for future lunar explorers, turning science fiction ideas into real possibilities. Fact 10. Lunar soil development. If you've ever seen a picture of the Moon's surface, you've probably noticed it's covered in a grey, dusty layer. That's lunar soil, or regolith, and it's much more than just dirt. Lunar soil formed over billions of years from meteorite impacts, volcanic activity, and the slow weathering of rocks. Unlike Earth soil, there's no organic material, no plants, no bacteria, just pulverized rock and tiny glass particles created by intense heat during impacts. Each crater, each tiny fragment tells a story of cosmic collisions. Lunar soil is also what astronauts had to contend with during Apollo missions. It's clingy, abrasive, and can get into every crack of a spacesuit or equipment. This regolith is like a record book of the Moon's history. Every layer holds clues about impacts, volcanic eruptions, and the subtle processes that shape the Moon over billions of years. When you walk across it in your imagination, you're stepping on history itself. Fact 11. Diameter of the Moon. When you look at the Moon in the night sky, it might seem like a small, gentle companion hovering above us. But in reality, it's enormous. The Moon's diameter is about 3,474 kilometers, which is roughly 1/4 the diameter of Earth. To put that in perspective, if Earth were the size of a basketball, the Moon would be about the size of a tennis ball. Despite its smaller size, the Moon has a huge presence. That relatively modest diameter is what allows it to orbit Earth so gracefully and even create spectacular solar eclipses. Its size is just right to perfectly cover the Sun from our point of view. No bigger, no smaller. A cosmic coincidence we often take for granted. Interestingly, the Moon's size is also linked to its formation. The giant impact hypothesis suggests that the debris that formed the Moon came from Earth's outer layers. That material coalesced into a satellite big enough to stay in orbit but small enough to cool relatively quickly compared to Earth. So, the next time you gaze at the Moon, remember that its seemingly gentle, small appearance hides a world over 3,400 kilometers across. It's massive enough to shape tides, influence life, and keep us dreaming about space, yet just the right size to remain a quiet, constant companion in the sky. Fact 12. Mass and gravity comparison with Earth. The Moon might look big, but it's only a fraction of Earth's mass. Its total mass is about 181 of Earth's, which is why its gravity is so much weaker. On the Moon, you would weigh only about 16% of what you do on Earth, so a 70-kilogram person here would weigh roughly 11 kilograms there, enough to hop and bounce like an astronaut in a slow-motion video. This lower gravity explains a lot about the Moon's surface. For example, dust kicked up by meteor impacts doesn't settle as quickly as on Earth, creating a soft, powdery layer of regolith. It also affects how volcanic eruptions occurred in the past, letting lava flow more smoothly and spread across large areas to form the Maria. Gravity is also why the Moon can't hold a thick atmosphere. Its weak pull allows gases to escape into space easily, which is why the Moon is a vacuum today. Without this low gravity, we might see weather patterns, clouds, or erosion, making the Moon look much more like Earth. So, even though the Moon's size seems substantial, its mass and gravity give it a unique identity, a quiet, lightweight companion that's more fragile than it appears. It's enough to shape our tides, guide explorers, and influence Earth, yet not enough to sustain life as we know it. Fact 13. Surface area of the Moon. You might think of the Moon as just a bright circle in the sky, but its surface is vast. Covering about 38 million square kilometers, the Moon's surface is roughly equivalent to the continent of Africa. That's a huge playground of craters, maria, mountains and valleys, all waiting to tell the story of billions of years of cosmic history. Each part of this surface has a tale. The maria, the dark lava plains, cover about 16% of the Moon, while the highlands, the bright rugged regions, make up the rest. Tiny craters peppered across the surface are reminders of relentless asteroid bombardment, and even the largest impact basins, like the South Pole Aitken Basin, stretch thousands of kilometers across, dwarfing many features on Earth. The Moon's surface area also influences exploration. Apollo astronauts only covered a tiny fraction, leaving most of it untouched. Modern orbiters now map the entire surface in detail, helping us understand the Moon's formation, evolution, and potential for future human bases. When you imagine the Moon up close, it's not just a glowing disk, it's a vast, textured world, a mix of smooth plains and jagged highlands, all packed into a familiar shape we've admired for millennia. Fact 14. Lunar equator versus poles. The Moon isn't perfectly uniform. Its equator and poles have some striking differences. The equator is relatively smooth and has more maria, while the poles are rugged, heavily cratered, and contain areas of permanent shadow. These shadowed regions are especially fascinating because they can trap ice, protecting it from the sun's heat. Temperature extremes also vary depending on latitude. The equator sees swings from 320 Celsius during the day to 173 degrees at night, while some polar craters remain in near constant cold, around 250 degrees. This difference makes the poles especially interesting for future lunar explorers seeking water ice. Additionally, the Moon's tilt is small, only about 1.5 degrees, so sunlight behaves differently at the poles compared to Earth. Some peaks get near continuous light, while deep craters stay in shadow. This combination of light and darkness is perfect for both solar power and ice preservation, creating ideal spots for potential lunar bases. So, the Moon's geography isn't just pretty, it's a blueprint for exploration, telling us where resources might exist and how different regions behave in the harsh lunar environment. Fact 15. Mountains on the Moon. When we imagine the Moon, we often think of craters and flat maria, but it also has towering mountains. Lunar mountains are mostly formed from massive impacts and crustal shifts. For example, the Montes Apenninus stretches over 600 kilometers and rises more than 5 kilometers high, rivaling some of Earth's peaks. These mountains are remnants of ancient collisions. When huge asteroids struck, they compressed the crust, sending material upward to form mountain ranges. Some peaks even border large basins, creating dramatic landscapes unlike anything on Earth. Mountains on the Moon also tell us about its crust. The rugged highlands are more mountainous than the smoother maria, showing the story of the Moon's molten past and slow cooling. Imagine walking across these peaks. Each rock, ridge and valley is a page of lunar history frozen in time. Even though the moon feels calm from Earth, its mountains are a reminder that this quiet satellite has experienced violent, awe-inspiring events, shaping every crater and ridge we see today. Fact 16. Craters and impact history. If you've ever looked closely at the moon, one thing jumps out immediately. Craters. Craters everywhere. Some are tiny, just a few meters across, while others are massive basins hundreds of kilometers wide. These craters are like scars on the moon's face, each one telling a story of cosmic collisions over billions of years. The moon has no atmosphere to slow down incoming meteoroids, so every impact, big or small, hits with full force. Some craters were formed during the moon's heavy bombardment period, around 4 billion years ago, when the solar system was chaotic and asteroids were constantly slamming into planets and moons. The result? A surface covered in impact marks that have largely stayed intact, because the moon lacks weather and plate tectonics to erase them. Interestingly, craters aren't just random holes. They can reveal the moon's history. Their size, shape, and distribution tell scientists about the frequency of impacts, the composition of meteoroids, and even the moon's internal structure. Some craters have central peaks, formed when the surface rebounds after a giant impact, while others are flat-bottomed or filled in by lava. Every crater is a snapshot of time. Looking at the moon, you're essentially reading a 4.5 billion-year-old diary of cosmic collisions, each mark preserving a chapter of the solar system's violent youth. And these craters connect to other features, like Maria and Rails, showing how impacts shape the moon's overall landscape. Fact 17. Maria, the dark plains. The dark, smooth patches on the moon are called Maria, which is Latin for seas. But don't be fooled, they aren't made of water. These plains formed billions of years ago when massive impacts cracked the moon's crust, allowing molten lava to flow into basins and harden. Maria are mostly found on the near side of the moon because the crust there is thinner, making it easier for lava to seep through. The largest, like Mare Imbrium and Mare Serenitatis, cover hundreds of kilometers and are visible from Earth with the naked eye. Their dark color comes from basalt, a dense volcanic rock that cooled after flowing into the basins. These plains give the moon its iconic appearance. They contrast beautifully with the bright highlands, creating the face we recognize as the man in the moon in some cultures. But Maria aren't just pretty, they also tell a story about the moon's volcanic past, its cooling process, and the aftermath of massive impacts. Without Maria, the moon would look completely different, a jagged, cratered surface lacking the smooth areas that break up its monotony. Next time you see the moon glowing in the night sky, remember that those dark patches are frozen rivers of ancient lava, quietly narrating a story from billions of years ago. Fact 18. Highlands, bright regions. In contrast to the dark Maria, the moon's highlands are bright, rugged, and heavily cratered. These areas represent the oldest parts of the lunar surface, formed shortly after the moon's crust solidified from the ancient magma ocean. Highlands are primarily composed of anorthosite, a light-coloured rock that reflects sunlight brilliantly. That's why they appear so striking from Earth. They're also incredibly mountainous, with peaks and ridges reaching several kilometers in height. The terrain is rough and chaotic because it hasn't been smoothed by lava flows like the Maria. The highlands are a window into the moon's past. They preserve evidence of heavy bombardment from billions of years ago, capturing the scars of early solar system chaos. Studying these regions allows scientists to understand the moon's crust formation, its internal composition, and even the conditions that existed when the moon was young and molten. So, when you admire the moon in the night sky, the bright patches aren't just pretty. They're ancient relics, telling the story of a world shaped by fire, impacts, and time. Fact 19. Rills, lunar valleys. Rills are narrow valleys or trenches that snake across the moon's surface, and they come in a few different types. Some are straight, likely caused by cracks in the crust, while others are sinuous, formed by ancient lava flows that carved winding paths. There are even some that appear as collapsed lava tubes, leaving deep grooves behind. These features may seem subtle compared to craters or Maria, but they reveal a lot about the moon's geological activity. Rills mark places where lava once flowed, or where the crust stretched and shifted, giving clues about volcanic processes and the moon's cooling history. Some rills are hundreds of kilometers long, proving that lunar lava could travel surprisingly far before solidifying. Rills also connect to other features. Many snake through Maria, suggesting that volcanic activity followed pre-existing structures, while others cross highlands, showing how impacts and lava reshaped the surface. They're quiet reminders that the moon was once a dynamic world, even if it appears frozen today. Next time you see a lunar map, tracing the winding paths of reals is like reading secret messages from the moon's molten past. Fact 20. Wrinkle ridges. Wrinkle ridges are low, elongated hills that wrinkle across the moon's Maria. They may seem minor compared to mountains or craters, but they're actually the surface's way of adjusting after lava flows cooled and contracted. As basaltic lava solidified, it shrank slightly, pushing the surface into folds and ridges. These ridges can stretch for hundreds of kilometers and offer clues about the moon's interior. Their patterns help scientists understand stress in the crust, past volcanic activity, and even the moon's thermal history. They're subtle signs that the moon's surface isn't static. It responds, bends, and shifts over time. In a way, wrinkle ridges are like tiny wrinkles on an ancient face, subtle but full of history. Observing them connects us to the moon's slow, quiet evolution, showing that even a seemingly dead world has a story written in its surface. Fact 21. Moon's orbit around Earth. The moon doesn't just hang in the sky like a stationary lantern. It's constantly moving, locked in an intricate dance with Earth. It travels in an elliptical orbit, meaning it's not a perfect circle but slightly stretched. This orbit takes the moon around our planet roughly every 27.3 days, creating the rhythm of lunar cycles we've observed for millennia. This orbit is what gives us the moon's phases. As the moon circles Earth, different portions of its sunlit side become visible, creating new moons, crescents, and full moons. But the orbit also affects tides. The moon's gravity pulls on Earth's oceans, creating bulges of water that shift as the moon moves. Without this orbital dance, our tides would be far less dramatic, and life on Earth might look very different. Interestingly, the moon's orbit isn't static. Over time, gravitational interactions with Earth are slowly pushing it farther away, about 3.8 centimeters per year. This gradual drift affects both Earth's rotation and the length of the day, making the moon a key player in the planet's long-term evolution. So, when you look up at the moon tonight, remember, it's not just hanging there, it's moving, orbiting, and shaping life on Earth in ways we often take for granted, quietly performing a cosmic waltz billions of years in the making. Fact 22. Orbital period, 27.3 days. The moon takes about 27.3 days to complete a full orbit around Earth, a period known as the sidereal month. But here's the tricky part. A full cycle of phases, from new moon to new moon, actually takes about 29.5 days, called the synodic month. That's because as the moon orbits, Earth is moving too, so the moon has to catch up to line up with the sun and Earth. This orbital period is why we can predict eclipses, tides, and the familiar rhythm of lunar phases. Ancient civilizations tracked the moon's movement meticulously, building calendars and agricultural schedules around its regular path. Even today, the moon's orbit is vital for navigation, astronomy, and planning space missions. Knowing the orbital period also explains why the moon's position in the sky changes slightly night by night. It's slowly travelling around us, a silent clock marking time in the heavens. And this steady motion ties into other fascinating features, like synchronous rotation, which ensures we always see the same side. So 27.3 days isn't just a number, it's the beat of the moon's rhythm, a cosmic timer that has influenced life on Earth for billions of years. Fact 23. Synchronous rotation. Why we always see one side. Ever notice that we always see the same face of the moon? That's thanks to something called synchronous rotation. The moon rotates on its axis at the same rate it orbits Earth, making one complete spin for every orbit. The result, the near side is always facing us, while the far side remains hidden. This isn't some magical coincidence. It's the result of tidal forces over billions of years. Early in its history, the moon rotated faster, but Earth's gravity tugged on it, gradually slowing its rotation until it locked into this synchronized pattern. It's a delicate balance of gravity and motion, a cosmic dance frozen in place. Synchronous rotation also explains why the moon's far side looks so different. Without frequent sunlight and with a thicker crust, volcanic activity was limited there, creating fewer maria and a more rugged surface. It's amazing to think that one subtle change in motion billions of years ago shaped the moon's entire appearance from our perspective. Fact 24. Lunar libration, slight wobble. Even though the moon is tidally locked, we don't see exactly 50% of its surface. We actually glimpse about 59% over time. That's thanks to lunar libration, a slight wobble caused by variations in the moon's orbit and tilt. It's a subtle rocking motion that lets us peek around the edges of the far side. There are 3 types of libration: longitudinal, latitudinal, and diurnal. Longitudinal libration comes from the moon's elliptical orbit, latitudinal from its tilted axis, and diurnal from the Earth's rotation, giving observers slightly different views. The result is a slow reveal of more terrain than you might expect. Libration is useful for scientists mapping the moon, because it allows detailed observation of areas near the limb that wouldn't otherwise be visible from Earth. So, while the moon seems unchanging, this gentle wobble shows it's still a dynamic participant in its orbital dance. Fact 25. Distance from Earth. The moon isn't sitting at a fixed distance from Earth. It orbits at an average of about 380,400 kilometers, roughly 30 times Earth's diameter. That distance varies slightly because its orbit is elliptical, ranging from about 363,000 kilometers at perigee, closest, to 4 or 5,000 kilometers at apogee, farthest. This distance affects what we see in the sky. When the moon is at perigee, we get a supermoon, appearing bigger and brighter. At apogee, it looks smaller, sometimes called a micromoon. The varying distance also influences tides and even the duration of solar eclipses. The moon's distance has slowly increased over billions of years due to tidal interactions with Earth. Long ago, it was much closer, making solar eclipses more frequent and more dramatic. As it drifts away, the moon quietly changes the dynamics of our planet in ways we're only beginning to fully understand. So when you admire the moon tonight, remember, it's not just floating in space, it's moving, drifting, and shaping life on Earth from a remarkable distance. Fact 26. Eccentricity of lunar orbit. If you think the moon travels in a perfect circle around Earth, think again. Its orbit is slightly elliptical, which means it's not a perfect circle but a stretched oval. Scientists call this shape eccentric, and it's measured by something called orbital eccentricity, which for the moon is about 0.055. That may not sound like much, but it makes a big difference. Because of this eccentricity, the moon's distance from Earth changes as it orbits. Sometimes it's closer, sometimes farther, and this affects its apparent size in the sky. When the moon is closer at perigee, we get a supermoon. When it's farther away at apogee, it looks smaller, a micromoon. Even tides are influenced by this changing distance, creating subtle variations in high and low tides. Eccentricity also plays a role in the moon's synchronous rotation and libration. The slight variations in speed caused by its elliptical orbit make the moon wobble gently, letting us peek at a bit more than half its surface over time. It's fascinating that such a small deviation from a perfect circle can create noticeable effects, both visually and scientifically. So next time you see the moon looking slightly bigger or smaller than usual, remember it's all thanks to this small but important orbital eccentricity, a reminder that even the moon's journey through space isn't perfectly simple. Fact 27. Inclination of orbit. The moon doesn't orbit perfectly along Earth's equator. Instead, its orbit is tilted by about 5 degrees relative to Earth's orbital plane around the Sun. This tilt, or inclination, might seem minor, but it has major consequences. Because of this 5-degree tilt, the moon usually passes above or below the Sun during what would otherwise be solar eclipses. Only when the moon, Sun, and Earth align at one of the 2 points where the orbital planes intersect do we get an eclipse. That's why solar eclipses are relatively rare events, even though the moon orbits Earth every month. Inclination also subtly affects the moon's path across the sky and the timing of tides. Ancient civilizations noticed these variations, building lunar calendars and predicting eclipses with remarkable accuracy. Even today, the moon's orbital tilt is a crucial factor for planning space missions and understanding its long-term gravitational relationship with Earth. So, a small 5-degree tilt explains a lot, from why eclipses don't happen every month, to how the moon's path affects our tides. It's a perfect example of how tiny cosmic details can create huge visible effects. Fact 28. Perigee and apogee, closest and farthest points. The Moon's elliptical orbit means it doesn't stay the same distance from Earth. The closest point in its orbit is called perigee, and the farthest is apogee. At perigee, the Moon can be about 363,000 kilometers away, appearing noticeably larger in the sky. At apogee, it stretches out to about 405,000 kilometers, looking smaller and dimmer. These variations aren't just visual. Tides are higher during perigee because the Moon's gravitational pull is stronger. This also explains why some eclipses are longer or shorter, depending on whether the Moon is at perigee or apogee. Supermoons, which occur when a full moon coincides with perigee, are a direct result of this orbital behavior. They give us stunningly bright, larger-looking moons, making the Moon's closest and farthest points something we can see with the naked eye. So perigee and apogee aren't just scientific terms, they're dynamic moments in the Moon's orbit that create visible changes and affect life on Earth in subtle but noticeable ways. Fact 29. Tidal locking. Explained. Ever wonder why the Moon always shows the same face to Earth? That's thanks to tidal locking. Essentially, Earth's gravity has gradually slowed the Moon's rotation until it matched its orbital period. One rotation equals one orbit, locking one side permanently toward Earth. This isn't instant. It took millions of years. Early on, the Moon rotated faster, but the constant tug of gravity stretched and slowed it down. It's a delicate balance. Now the Moon's far side is hidden, while the near side gets all the sunlight and attention from us. Tidal locking also affects Earth. The Moon's gravitational pull creates tides, slows Earth's rotation, and gradually increases the length of our days. It's fascinating to think that this subtle, gravitational dance billions of years ago shaped both bodies in ways we still experience today. Fact 30. Effects of Moon on Earth's rotation. The Moon doesn't just orbit passively, it affects Earth itself. Its gravitational pull creates tides, but it also slows our planet's rotation. Billions of years ago, Earth's day might have been just 6 or 8 hours long. Today, thanks to tidal friction with the Moon, a day is 24 hours. This slowing is gradual, about 1.7 milliseconds per century, but over millions of years it adds up. The process also pushes the Moon slightly farther away from Earth. Essentially, Earth and the Moon are locked in a slow, mutual dance. The Moon shapes our day length, and in return, Earth gradually nudges the Moon outward. The Moon's influence on Earth is subtle but profound, affecting tides, rotation, and even the stability of our planet's axis. Without the Moon, life on Earth might be very different, with shorter days, weaker tides, and less stable climates. It's a quiet partnership that has lasted billions of years and continues today. Fact 31. New Moon explained. The new moon is a curious phase because, ironically, you can't really see it. During this phase, the Moon is positioned between Earth and the Sun, so the side facing us is completely in shadow. From our perspective, it almost disappears from the sky, blending into the darkness of night. But the new moon isn't just empty space, it's a critical start of the lunar cycle. Ancient civilizations used this phase to mark the beginning of months, planting seasons, and important rituals. Even today, calendars and festivals in some cultures still rely on the new moon as a starting point. Interestingly, the new moon is also the best time for astronomers to observe distant stars and galaxies. With the moon out of the way, its light doesn't interfere with telescopes, making the night sky clearer and darker than at other times. So while it may seem like nothing is happening during the new moon, it's actually a quiet but essential moment in the moon's monthly rhythm, a reset, a shadowed pause, and a reminder that even the invisible parts of cycles are important. Fact 32. Waxing crescent. After the new moon comes the waxing crescent, when a thin sliver of light begins to appear on the moon's edge. Waxing means growing, and this crescent is the moon slowly waking up, stretching its glow across the night sky. This phase is visible just after sunset, often hanging low near the horizon. It's a delicate, almost magical sight. The crescent is thin enough to feel fragile, yet it signals the moon's steady journey toward fullness. Ancient observers often used the waxing crescent as a symbol of growth, hope, and new beginnings. The waxing crescent also shows the play of shadows across the moon's surface. Craters and mountains near the crescent's edge become highlighted in sharp relief, giving astronomers a chance to study the terrain in dramatic contrast. So this seemingly small slice of light is actually full of life, history and science. It reminds us that every stage of the moon has a story, even the brief moments when it's just beginning to show itself. Fact 33. First quarter. The first quarter moon is when half of the moon is illuminated and half remains in shadow. It's called quarter because it occurs about a week after the new moon, marking 1/4 of the way through the lunar cycle. This phase is perfect for sky watchers. The contrast between light and shadow makes craters and mountains stand out dramatically along the terminator, the line dividing day and night on the moon. It's almost like the moon is putting on a show just for us. The first quarter also has symbolic significance in many cultures, often associated with decisions, action and progress. It's the moon's way of signalling the journey has begun and there's momentum building. From a practical perspective, the first quarter is a favourite for amateur astronomers, offering detailed views of the lunar surface without being too bright or too faint. Fact 34. Waxing gibbous. After the first quarter comes the waxing gibbous, when most of the moon is illuminated but not quite full. The gibbous shape is rounded and expansive, signalling that the moon is almost at its peak brightness. During this phase, the moon rises later in the afternoon and dominates the evening sky. Its glow is stronger, casting soft shadows on the ground, making familiar landscapes look otherworldly. Craters, valleys and ridges are still visible near the terminator, giving astronomers and enthusiasts plenty to explore. The waxing gibbous is a time of anticipation, just days away from the full moon. Cultures around the world have historically linked it to preparation, growth, and the nearing of fruition. It's amazing how this phase blends beauty and science. The moon is nearly full, yet its details are still sharp enough to study, and its presence in the night sky evokes emotion, wonder and curiosity. Fact 35. Full moon. The full moon is the moon at its brightest and most complete, fully illuminated by the sun. It rises at sunset and sets at sunrise, dominating the night sky with its silvery glow. This is the moon at its peak, a luminous spectacle that has fascinated humans for thousands of years. Full moons have inspired myths, legends and traditions across cultures, from werewolves to harvest festivals. Astronomers love it too, though it's not ideal for studying surface details because the bright light washes out shadows. Still, it's perfect for observing the moon's overall shape, maria, and highlands from Earth. Interestingly, the full moon's position in its orbit affects tides. It's when Earth, Moon and Sun align, creating spring tides, higher and lower than average. So the full moon isn't just beautiful, it also impacts our oceans and rhythms of life. Every full moon is a reminder of the moon's enduring presence, a silent companion marking time, beauty, and natural cycles in the night sky. Fact 36. Waning gibbous. After the full moon shines at its brightest, it begins to shrink, entering the waning gibbous phase. Waning means decreasing, and during this time the moon gradually loses its illuminated portion. Most of it is still visible, but each night it appears slightly smaller, like a glowing coin slowly fading in the sky. This phase rises later in the evening and sets in the early morning, dominating the night but slowly retreating. Craters and surface details near the terminator, the line between light and shadow, are still visible, making it an excellent phase for lunar observation. Scientists often study the moon during this period to trace features and compare them to other phases. Culturally, the waning gibbous has been associated with reflection, letting go, and releasing what's no longer needed. Ancient civilizations used it as a reminder that life, like the moon, has cycles of growth and decline. It's fascinating how the moon's simple shifting light carries both scientific insight and human meaning, connecting us to its rhythms every night. Fact 37. Last quarter. The last quarter moon, sometimes called the third quarter, is when half of the moon is illuminated and the other half in shadow, opposite of the first quarter. Occurring roughly 3 weeks after the new moon, it marks a turning point in the lunar cycle. During this phase, the moon rises around midnight and sets around noon, making it visible in the morning and early afternoon. It's a perfect time for observing surface details along the terminator, because the sharp contrast highlights craters and ridges beautifully. Symbolically, the last quarter has been associated with reflection, reassessment, and preparation for new beginnings. It's the moon's gentle reminder that every cycle eventually returns to its starting point. Scientifically, this phase completes the moon's visibility cycle before it returns to new moon, demonstrating the continuous, predictable rhythm of our celestial companion. Fact 38. Waning crescent. The final phase of the lunar cycle is the waning crescent, when only a thin sliver of the moon is visible. Rising just before sunrise, it's often the last glimpse of the moon before the new moon begins again. This delicate crescent is a subtle and poetic sight, almost fading into daylight. It's historically been seen as a time of rest, reflection, and preparation for new cycles. Astronomers can still use this phase to study the moon's surface near the terminator, but its thin illumination creates long, dramatic shadows, emphasizing surface features. The waning crescent reminds us that even endings are beautiful. It's quiet, unassuming, and a natural part of the moon's steady cycle, connecting the end of one month to the beginning of another. Fact 39. Lunar cycle duration. From new moon to new moon, the lunar cycle lasts about 29.5 days, called the synodic month. This cycle is slightly longer than the moon's orbital period of 27.3 days, because Earth is also moving around the sun, so the moon has to catch up to realign with Earth and the sun. This rhythm has guided humans for millennia. Ancient calendars, agricultural cycles, and religious events were all tied to the lunar cycle. The moon's phases provide a natural clock, quietly marking time for everything from planting crops to planning festivals. The cycle also affects tides, animal behavior, and even human culture. It's a perfect example of how celestial mechanics influence life on Earth, reminding us that the moon isn't just a distant object, it's a constant companion shaping our world. Fact 40. Supermoon phenomenon. A supermoon occurs when a full moon coincides with perigee, the point in its orbit closest to Earth. This makes the moon appear larger and brighter in the sky, sometimes up to 14% bigger than a typical full moon. Supermoons are spectacular to observe, lighting up landscapes and creating dramatic reflections on water. They also subtly influence tides, producing slightly higher high tides and lower low tides than usual. The phenomenon is a visual reminder of the moon's elliptical orbit and changing distance from Earth. While not rare, supermoons capture attention because they're both beautiful and scientifically interesting, linking observation, gravity, and orbital mechanics in one luminous event. Fact 41. Solar eclipse basics. A solar eclipse is one of nature's most dramatic spectacles. It happens when the moon passes directly between Earth and the sun, casting a shadow on our planet and blocking sunlight in specific areas. From the ground, it can look like the sun is disappearing, leaving the sky dim and eerie for a few minutes. Solar eclipses come in different types. Sometimes the moon covers the sun completely, creating a total solar eclipse. Other times, it only blocks part of the sun, producing a partial eclipse. There's even the rare annular eclipse, where the moon appears slightly smaller than the sun, leaving a glowing ring or ring of fire in the sky. The fascinating part is that the moon and sun appear almost the same size from Earth, even though the sun is vastly larger. This is a coincidence of distance and size making solar eclipses possible. Ancient civilizations viewed them with awe and sometimes fear, seeing them as mysterious or powerful natural events. Today, we understand the mechanics and can predict them centuries in advance, turning what was once mysterious into an observable scientific marvel. A solar eclipse is brief but unforgettable. It reminds us of the delicate cosmic dance between Earth, Moon, and Sun, and how precise alignment can create moments of breathtaking beauty. Fact 42. Lunar eclipse basics. A lunar eclipse occurs when Earth passes directly between the Sun and the Moon, casting its shadow on the Moon's surface. Unlike a solar eclipse, lunar eclipses are safe to view with the naked eye, and they can last for hours, offering plenty of time to appreciate the spectacle. During a lunar eclipse, the Moon gradually darkens as it enters Earth's shadow. Depending on the alignment, it can appear partially or fully obscured. The Moon doesn't disappear entirely because some sunlight bends through Earth's atmosphere, casting a reddish glow on its surface. This blood moon effect has inspired myths and legends for centuries, symbolizing mystery, change, and even prophecy. Lunar eclipses happen only during a full moon. But not every full moon experiences one. The moon's orbital tilt means it usually passes above or below Earth's shadow, so perfect alignment is relatively rare. Ancient astronomers used these eclipses to understand celestial mechanics, helping them map the moon's orbit and predict future events. In short, a lunar eclipse is a subtle, beautiful reminder that Earth and Moon are locked in a cosmic dance, casting shadows and reflections that tell the story of their gravitational relationship. Fact 43. Total lunar eclipse. A total lunar eclipse is when the entire moon passes through Earth's umbra, the darkest part of its shadow. During this time, the moon often turns a deep coppery red, earning it the nickname Blood Moon. The colour comes from sunlight bending through Earth's atmosphere and filtering out blue light, leaving red and orange hues. Totality can last up to 1 hour and 40 minutes, depending on the moon's path through the shadow. Unlike solar eclipses, you can watch the entire event safely without special equipment. Many people find total lunar eclipses mesmerizing because the transformation is gradual, dramatic, and unpredictable in its exact intensity of color. Culturally, total lunar eclipses have inspired fear, celebration, and awe across civilizations. Ancient civilizations often linked them to omens or messages from the divine, while modern astronomers use them to study the moon's surface, Earth's atmosphere, and orbital mechanics. A total lunar eclipse is more than a visual spectacle. It's a live demonstration of the Sun-Earth-Moon relationship, gravity and light, unfolding in real time for everyone on the night side of Earth. Fact 44. Partial lunar eclipse. During a partial lunar eclipse, only a portion of the moon enters Earth's umbra. This creates a striking contrast between the bright, fully illuminated part and the shadowed region, which often appears reddish or dark grey. Partial eclipses are more common than total ones, and they provide excellent opportunities for observation. The shadow slowly creeps across the moon's surface, making the event feel dynamic, almost like watching a celestial painting being shaded in layers. Even though it's partial, the experience can be mesmerizing. Ancient observers were fascinated by the gradual disappearance of part of the moon, interpreting it as cosmic drama. Today we know it's simply the result of geometry and orbital alignment, but the beauty and subtlety remain. Partial lunar eclipses show that the moon's interaction with Earth's shadow is not always all or nothing. They highlight the delicate, shifting alignment that creates these predictable, yet enchanting celestial events. Fact 45. Penumbral lunar eclipse. The penumbral lunar eclipse is the most subtle type, occurring when the moon passes through Earth's outer shadow, called the penumbra. Unlike total or partial eclipses, the dimming is gentle, sometimes barely noticeable to the naked eye. During this eclipse, the moon may appear slightly darker on one side, as if someone has softly brushed a shadow across its surface. Because the effect is subtle, it can be easy to miss, but it's still a real eclipse, and it follows the same principles of alignment that govern all lunar eclipses. Penumbral eclipses are useful for astronomers studying how Earth's shadow interacts with light, and how subtle changes in brightness can reveal information about both Earth and the moon. They also demonstrate that even minor alignments in space can create measurable effects, showing the precision of celestial mechanics. Even though it's understated, a penumbral lunar eclipse reminds us that not all cosmic events are dramatic. Sometimes, subtlety tells the most interesting stories. Fact 46. Blood moon explanation. The term blood moon refers to the reddish appearance of the moon during a total lunar eclipse. When Earth comes between the sun and the moon, it casts a shadow on the lunar surface. But instead of going completely dark, the moon often glows a coppery red. Why red? It's all about sunlight passing through Earth's atmosphere. As light filters through, shorter blue wavelengths scatter out, leaving longer red and orange wavelengths to bend toward the moon. It's the same reason sunsets and sunrises appear red on Earth. During a blood moon, the moon becomes a glowing celestial lantern, bathing the night sky in surreal colours. The phenomenon has inspired awe and sometimes fear throughout history. Even today, photographers, sky watchers, and casual observers are captivated by the moon's dramatic transformation, reminding us of the invisible connections between Earth, Sun, and Moon. Fact 47. Frequency of eclipses. Lunar eclipses are fairly common, occurring at least twice a year somewhere on Earth. However, total lunar eclipses are less frequent. They only happen when the Sun, Earth, and Moon align perfectly, allowing the Moon to pass fully into Earth's umbra. Partial and penumbral eclipses happen more often, but their visibility depends on location and timing. Not every lunar eclipse is visible from every part of Earth, so while the Moon may darken somewhere, people across the globe may miss the event entirely. The frequency is governed by the Moon's orbit. Because it's tilted about 5 degrees relative to Earth's orbit around the Sun, perfect alignments are rare. This tilt ensures that eclipses remain special events, moments of cosmic precision we can predict years in advance. Fact 48. Why lunar eclipses are red. The reddish hue of lunar eclipses is a fascinating optical trick caused by Earth's atmosphere. As sunlight passes through our atmosphere, blue light scatters out, leaving red and orange light to bend around the planet and illuminate the Moon. The exact shade depends on atmospheric conditions. Dust, volcanic ash, and pollution can deepen the red or create copper, orange, or even brown tones. So each blood moon is unique, reflecting not only the celestial alignment, but also the state of Earth's atmosphere at that moment. This explains why lunar eclipses have been observed as mysterious or ominous in ancient times. The changing colour can look dramatic and unpredictable, sparking imagination and myth. Fact 49. Ancient eclipse records. Humans have been observing lunar eclipses for thousands of years. Ancient civilizations in Babylon, China, and Egypt carefully documented these events, often linking them to kings, omens, and seasonal calendars. Babylonian astronomers used eclipse records to predict future eclipses, showing an early understanding of orbital cycles and celestial mechanics. In China, historical texts describe eclipses as dragons eating the moon, highlighting how cultural interpretation and scientific observation often coexisted. These ancient records are valuable today. By studying them, scientists can trace the moon's orbital history, understand tidal effects over millennia, and even validate modern astronomical models. Fact 50. Lunar eclipses in mythology. Lunar eclipses have always carried a sense of mystery and wonder. Many cultures created stories to explain the moon's sudden darkening or red glow. Some imagined celestial dragons or wolves devouring the moon, while others saw it as a powerful natural event or a warning of significant change. In some Native American traditions, a blood moon was a time for reflection or ceremony. In Hindu folklore, it is often interpreted as the demon Rahu swallowing the moon. Even in medieval Europe, eclipses inspired fear, superstition, and cautionary tales. These stories reveal how deeply humans connect with the moon. While science now explains lunar eclipses, the tales remind us that the moon has always been more than a celestial body. It's a mirror of imagination, culture, and our fascination with the skies. Fact 51. Regolith, moon soil layer. If you were to land on the moon, the first thing your boots would touch is regolith, the fine layer of loose, dusty soil covering the lunar surface. This isn't like Earth soil. There's no moisture or organic material, just crushed rock, tiny fragments of minerals, and glassy particles created by countless impacts over billions of years. Regolith forms from a constant barrage of meteoroids, which pulverize the surface and mix with older rock layers. Even micrometeorites, smaller than a grain of sand, play a role by gradually grinding down rocks. Over time, these repeated impacts produce a powdery, yet surprisingly sharp and abrasive, layer that can be up to several meters thick in some areas. Apollo astronauts noticed that regolith sticks to everything because of its electrostatic properties. The moon's environment causes dust to cling to suits, tools, and equipment, making it one of the trickiest aspects of lunar exploration. Despite being just dirt, regolith tells a deep story. It's a record of every impact, volcanic eruption, and cosmic event that shaped the moon's surface. Fact 52. Lunar dust properties. Lunar dust is not your everyday dirt. It's incredibly fine, jagged, and abrasive, almost like powdered glass. Because the moon has no atmosphere or weather to smooth particles, every grain is sharp-edged, formed by impacts and micrometeorite explosions. This dust poses challenges for astronauts. During the Apollo missions, it stuck to spacesuits, infiltrated equipment, and even irritated eyes and lungs. Despite its nuisance, lunar dust is scientifically valuable. Its composition provides clues about the moon's history, volcanic activity, and the impacts that created it. Interestingly, the dust carries tiny amounts of solar wind particles embedded in its grains, acting like a cosmic time capsule. Studying these particles allows scientists to understand how the sun has interacted with the moon over billions of years. Lunar dust may be fine and annoying, but it's also a precious record of the moon's environmental story. Fact 53. Apollo mission samples. The Apollo missions didn't just take astronauts to the moon, they brought back a treasure trove of samples. Between 1969 and 1972, Apollo astronauts collected over 380 kilograms of lunar rocks, soil, and core samples, allowing scientists to study the moon up close without leaving Earth. These samples included regolith, basalt, and anorthosite rocks, each telling a different story. Basalts revealed volcanic activity, while anorthosites showed how the lunar crust formed. Even tiny dust particles helped us understand the effects of space weathering and micrometeorite impacts. Apollo samples revolutionized our knowledge. They confirmed theories about the moon's origin, gave insight into its geological processes, and allowed precise radiometric dating, proving the moon is roughly 4.5 billion years old. Every rock and grain collected is a piece of a larger lunar puzzle, helping humanity understand our closest celestial neighbour. Fact 54. Lunar rocks. Basalt versus anorthosite. The moon's surface is dominated by two main rock types, basalt and anorthosite. Basalt is a dark volcanic rock, found mostly in the Maria, formed by ancient lava flows that filled impact basins. Its smooth texture and dense composition contrast sharply with the rugged highlands. Anorthosite, on the other hand, is a bright light-coloured rock that makes up the lunar highlands. It formed early in the moon's history when a global magma ocean crystallized, floating lighter minerals to the surface. These rocks preserve the moon's ancient past, acting as time capsules from over 4 billion years ago. The contrast between basalt and anorthosite gives the moon its familiar appearance from Earth, dark plains against bright highlands. Studying these rocks tells us not just about volcanic activity, but also about the moon's formation, cooling history, and even how impacts reshaped the landscape. Fact 55. Volcanic features on the moon. The moon may seem quiet today, but billions of years ago, it was volcanically active. Lava flowed across impact basins, creating the smooth Maria we see from Earth. Some eruptions formed sinuous rills, winding channels where molten lava carved paths before cooling. Other volcanic features include domes, small rounded hills formed by slow lava extrusion, and wrinkle ridges, created as lava cooled and contracted. These features are evidence that the moon was once a geologically dynamic world, with heat and pressure shaping its surface. Volcanic activity slowed dramatically as the moon cooled, but traces remain, preserving the story of its fiery youth. Observing these features today allows scientists to understand the moon's interior, its thermal history, and the ancient forces that shaped its face. Fact 56. Lunar Rills Formation. If you look closely at the moon's surface, you'll notice long, narrow channels called rills. These lunar valleys are fascinating because they reveal the moon's volcanic and tectonic past. Rills come in a few types: sinuous, straight, and arcuate, each telling a different story. Sinuous rills often resemble winding riverbeds, but instead of water, they were carved by flowing lava billions of years ago. Lava would snake across the surface, eroding paths as it cooled, leaving behind these striking channels. Straight rills are thought to form from tectonic forces, cracks in the crust caused by stretching or contraction. Arcuate rills, gently curved, often appear along the edges of large impact basins, where the surface adjusted after massive collisions. Rills are more than just pretty features. They allow scientists to understand how the moon's crust behaved, how lava flowed, and how impacts reshaped the surface. Observing these ancient channels is like reading pages of the moon's geological diary, providing insight into processes that shaped our closest neighbour. Fact 57. Moonquakes. Causes and effects. The moon isn't entirely still. It experiences moonquakes, similar to earthquakes on Earth, but generally less intense. Some are caused by tidal forces from Earth, which stretch and squeeze the Moon as it orbits. Others result from meteoroid impacts or thermal expansion and contraction as the surface heats in sunlight and cools in darkness. Deep moonquakes, caused by tidal stress, can shake the Moon for over 10 minutes, much longer than most earthquakes on Earth. These tremors, while mild compared to terrestrial quakes, reveal that the Moon has a partially flexible interior and not just a rigid dead crust. Understanding moonquakes is crucial for future lunar bases. If humans return to the Moon for extended stays, engineers need to design habitats that can withstand these subtle but real tremors. Moonquakes remind us that even a seemingly lifeless world is still active, responding to gravitational forces and the occasional cosmic impact. Fact 58. Micrometeorite. Impacts. The Moon is constantly bombarded by micrometeorites, tiny fragments of rock and dust travelling at incredible speeds. Unlike Earth, the Moon has no atmosphere to burn up these particles, so even the smallest impact leaves a mark on its surface. Over billions of years, countless micrometeorites have shaped the regolith, creating tiny craters and glassy particles. These small impacts also slowly break down surface rocks into fine dust, contributing to the Moon's unique soil layer. Micrometeorite impacts are a reminder of the Moon's exposure to space. Even today, the surface is being sculpted minute by minute. Studying these tiny collisions helps scientists understand surface aging, space weathering, and the hazards future astronauts may face. Fact 59. Magnetic anomalies. Unlike Earth, the Moon doesn't have a global magnetic field, but it does have localized magnetic anomalies. Certain regions, often linked to ancient lava flows or large impacts, exhibit stronger magnetic properties than surrounding areas. These anomalies may be remnants of an early magnetic field or the result of electrically charged particles interacting with surface rocks. They offer scientists clues about the Moon's ancient interior, how it cooled, and how its early core may have generated magnetic forces. Magnetic anomalies are more than scientific curiosities. They could influence how lunar dust behaves, as charged particles interact with these fields and may even affect instruments used for exploration. They hint that the Moon, though quieter than Earth, still has a hidden complexity beneath its surface. Fact 60. Temperature extremes. The Moon experiences some of the most extreme temperatures in the solar system. Without a protective atmosphere, its surface swings from blistering heat to freezing cold. During the lunar day, temperatures can soar above 127 degrees, 260 degrees, while at night they plummet below 173°, 280°. These extremes affect everything on the Moon: rock expansion and contraction, regolith formation, and even the design of spacesuits and lunar habitats. Apollo astronauts had to plan activities carefully, as exposure to sunlight or shadow could quickly become dangerous. Temperature swings also influence lunar exploration technology, as rovers, instruments, and habitats must endure both scorching heat and freezing cold. The Moon's extremes are a daily reminder that its environment is harsh, beautiful, and unforgiving, all at once. Fact 61. Ice at lunar poles. For a long time, scientists thought the Moon was completely dry, but today, we know that ice exists at its poles, hidden in permanently shadowed craters where sunlight never reaches. These craters act like natural freezers, keeping water ice stable for millions or even billions of years. This ice isn't like the snow we see on Earth. It's often mixed with lunar soil and may appear in patches rather than large sheets. Despite being small, it's a game changer for exploration. Ice at the poles could provide water for drinking, oxygen for breathing, and even hydrogen for fuel. Future lunar bases could use these natural reserves to survive without constantly transporting resources from Earth. The discovery of ice has transformed how we think about the Moon. It's no longer just a dry, barren rock. It's a place that might support human life with careful planning and technology. Fact 62. Evidence from Chandrayaan-1, India's Chandrayaan-1 mission, played a key role in confirming lunar water. Launched in 2008, it carried instruments designed to detect hydrogen and water molecules. One of the most exciting discoveries came when scientists detected signatures of water and hydroxyl molecules across the lunar surface, especially near the poles. These findings were groundbreaking because they provided direct evidence of water on the Moon for the first time. Chandrayaan-1's observations changed decades of assumptions, proving that lunar ice isn't just theoretical, it's real and measurable. The mission also highlighted the importance of using remote sensing and advanced instruments to study distant worlds. Chandrayaan-1 didn't land on the Moon, yet it fundamentally changed our understanding of lunar resources and opened the door for future missions to exploit these reserves. Fact 63. Lunar water in craters. Some of the most promising sources of water are craters at the Moon's poles, permanently shadowed regions where sunlight never penetrates, trap water ice over eons. These craters act like natural cold storage units, preserving ice in a stable state despite the harsh lunar environment around them. Explorers and scientists hope these craters could be mined for water to support astronauts, provide oxygen, and even generate rocket fuel. Robotic missions and orbiters continue to map these regions, revealing how much ice exists and where it might be most accessible. Even small amounts of ice in these craters could revolutionize human exploration, reducing the need to carry heavy water supplies from Earth and making long-term lunar colonies feasible. Fact 64. Origins of lunar water. The Moon's water didn't come from a single source. Some likely arrived from comets and asteroids, which carried ice and deposited it during impacts. Solar wind also contributes by interacting with surface minerals, creating hydroxyl molecules. Over billions of years, this water accumulated, especially in permanently shadowed regions near the poles. Understanding its origins helps scientists predict where ice might be concentrated and how it interacts with the lunar surface. It also informs theories about how water may have arrived on other rocky worlds in the solar system, including Earth. Fact 65. Importance for future colonies. Water on the Moon is more than a scientific curiosity. It's essential for human colonization. Ice can be converted into drinking water, oxygen, and hydrogen for fuel, reducing the cost and difficulty of transporting resources from Earth. Access to water could make permanent lunar bases viable, supporting astronauts for months or even years. It also opens possibilities for agriculture, life support, and fuel production, turning the Moon into a stepping stone for deeper space exploration. The discovery of water ice makes the Moon more than a barren rock. It's a potential hub for humanity's next great adventure, demonstrating how even small resources can have enormous implications for survival and exploration. Fact 66. Solar wind interactions. Even though the Moon lacks a global magnetic field or thick atmosphere, it isn't completely isolated from space. The solar wind, a stream of charged particles from the Sun, interacts constantly with the lunar surface. Hydrogen ions from the solar wind can bond with oxygen in lunar minerals, creating hydroxyl molecules, a form of water. This process may seem subtle, but over millions of years it has contributed to the Moon's sparse water reserves. It also causes the lunar soil, or regolith, to become electrically charged, which makes dust cling stubbornly to surfaces, spacesuits, and equipment. Astronauts from the Apollo missions describe this dust as sticky and abrasive, complicating daily activities. Understanding solar wind interactions is critical for future lunar missions. Not only does it explain part of the Moon's water cycle, but it also affects radiation exposure and surface chemistry, helping scientists design habitats and technology that can withstand the harsh environment. The Moon, even without an atmosphere, is never truly passive. Solar wind ensures it's alive with subtle, ongoing processes. Fact 67. Water as rocket fuel. One of the most exciting possibilities for lunar water is turning it into rocket fuel. Water ice can be split into hydrogen and oxygen through electrolysis. Hydrogen acts as fuel, and oxygen as an oxidizer, forming the essential components for rocket propulsion. This capability could transform space travel. Instead of carrying all fuel from Earth, spacecraft could refuel on the Moon, making missions to Mars and beyond more feasible. Lunar bases could serve as fueling stations in space, turning the Moon into a launch pad for humanity's expansion into the solar system. It's not just science fiction. Engineers are already planning systems that could extract water, process it, and store it safely for rockets. The presence of ice at lunar poles makes this concept increasingly realistic, and it's one reason why lunar exploration has become such a hot topic in modern space programs. Fact 68. Mining possibilities beyond fuel, lunar mining could provide a variety of resources. Regolith contains metals like aluminum, titanium and iron, while polar ice offers water for life support. Extracting these resources will be challenging, but advances in robotics, 3D printing and automated processing make it increasingly feasible. Mining on the Moon isn't just about human survival. It could also support infrastructure for telescopes, habitats and research stations. By using local resources, missions can reduce reliance on Earth, making long-term exploration more sustainable. Lunar mining could be the first step toward humanity becoming a multiplanetary species. Fact 69. Lunar soil hydration. Hydration in lunar soil refers to the presence of water molecules bound to minerals. Even outside permanently shadowed craters, tiny amounts of water exist in the regolith, formed partly through solar-wind interactions. This water is subtle, often only detectable with advanced instruments, but it's widespread. Lunar soil hydration is crucial for understanding the Moon's water cycle, predicting where ice might accumulate, and planning sustainable use for human explorers. It also provides clues about how water is distributed on other airless worlds. Fact 70. Seasonal variations. The Moon experiences subtle seasons, though they aren't like Earth's. Changes in sunlight angles at the poles affect temperature extremes and the stability of water ice in permanently shadowed regions. Some areas may gain or lose tiny amounts of surface ice depending on these variations. Understanding seasonal effects is important for mission planning. It affects solar power availability, temperature regulation for habitats, and accessibility to ice deposits. Even on a seemingly static world, the Moon has rhythms that explorers must respect, showing that time and environment shape its surface in small but meaningful ways. Fact 71. Tides, caused by the Moon. Every time you watch the ocean's waves rise and fall, you're witnessing the Moon's invisible hand at work. The Moon's gravity pulls on Earth's oceans, creating the familiar high and low tides. While the Sun also plays a role, the Moon's effect is stronger because it's much closer to Earth. Tides are more than just a coastal spectacle. They influence ecosystems, marine life, and even human activity. Many creatures, from crabs to coral, rely on tidal rhythms for feeding and breeding. Ancient humans also tracked tides, timing fishing and navigation around their predictable patterns. It's fascinating to think that the Moon, a lifeless rock hundreds of thousands of kilometers away, can move water across entire oceans. The tides are a constant reminder of our planet's connection to its celestial companion and the subtle ways gravity shapes life on Earth. Fact 72. Tidal bulge effect. As the Moon's gravity pulls on Earth's oceans, it creates a bulge, a slight stretching of water toward the Moon. This tidal bulge isn't fixed. It lags slightly behind the Moon's position because Earth rotates faster than the Moon orbits. The bulge explains why there are generally 2 high tides and 2 low tides each day. It also affects Earth's crust, subtly flexing the solid ground beneath the oceans. Scientists study these effects not just to understand tides, but also to track Earth's rotation and how the planet responds to gravitational forces. The tidal bulge demonstrates the interplay between motion, gravity, and time. Even though the Moon seems distant, its pull stretches Earth in ways we can see and measure every day. Fact 73. Earth's rotation. Slowing. The Moon's influence doesn't stop at tides. It's gradually slowing Earth's rotation. As the tidal bulge moves ahead of the Moon, gravitational interactions transfer energy from Earth's spin to the Moon's orbit. This process lengthens our days by tiny increments over millions of years. Long ago, Earth's day was only about 18 hours. Over time, it stretched to 24 hours due to the Moon's gravitational pull. This slowing rotation affects everything from climate patterns to biological rhythms, illustrating how our planet's natural processes are intertwined with its celestial companion. Fact 74. Moon's recession, moving away. As energy transfers from Earth's rotation to the Moon's orbit, the Moon slowly drifts away from us, about 3.8 centimeters per year. This recession has been ongoing for billions of years and will continue for the foreseeable future. Though gradual, this movement has long-term consequences. It changes tidal patterns, affects Earth-Moon dynamics, and subtly alters how we experience night and day. Future astronomers and space missions will observe these shifts, providing insight into orbital mechanics and the evolution of planetary systems. The moon moving away reminds us that even seemingly fixed celestial objects are in constant motion, participating in a slow cosmic dance that shapes both our planet and its companion. Fact 75. Influence on climate and evolution. The moon's gravitational pull, tides, and stabilizing influence have shaped life on Earth in profound ways. Tides created intertidal zones, nurturing ecosystems where early life thrived. The moon's stabilizing effect on Earth's axial tilt keeps climates relatively stable, preventing extreme swings that could hinder evolution. Without the moon, Earth might wobble unpredictably, leading to chaotic seasons and potentially making life less hospitable. Its presence helped create a steady environment where ecosystems could develop and species could adapt. In short, the moon isn't just a bright object in the sky, it's a silent architect of life, influencing oceans, climates, and evolutionary pathways across billions of years. Its gravitational pull subtly guides the rhythms of the natural world, demonstrating the deep connection between Earth and its celestial partner. Fact 76. Historical calendars, based on the moon. Long before modern clocks and calendars, humans looked to the moon to mark time. Lunar cycles, phases from new moon to full moon and back, provided a natural rhythm for months. Ancient civilizations, including the Babylonians, Egyptians, and Chinese, built calendars based on these cycles, tracking agricultural seasons, religious festivals, and ceremonial events. The moon's predictable cycle helped early societies organize life. Farmers knew when to plant and harvest, sailors gauged tides for safe navigation, and communities celebrated rituals in sync with lunar events. Even today, some cultures still follow lunar calendars for religious holidays, like Ramadan in Islam or the Lunar New Year in East Asia. Using the moon as a calendar shows how intimately humans have been connected to the sky. Its phases became a natural clock, quietly influencing daily life for thousands of years. The moon isn't just a celestial body, it's a historical timekeeper that shaped civilization. Fact 77. Lunar impact on animal behavior. The moon doesn't just guide humans, it influences animal behavior too. Many marine creatures, including corals, fish, and crabs, time spawning with lunar cycles, using the light and tides as environmental cues. Birds and nocturnal animals also adjust activity levels based on moonlight. For example, some predators hunt more actively during full moons when visibility is higher, while prey species may hide more to avoid detection. Even insects and amphibians respond to lunar brightness, affecting feeding, migration, and reproduction patterns. This subtle influence highlights the moon's role beyond tides and calendars. It's a biological clock. For countless species, lunar rhythms are woven into survival strategies, demonstrating how celestial mechanics impact life on Earth in ways we don't always notice. Fact 78. Lunar myths and legends. Across the world, the moon has inspired stories, myths, and legends. Ancient cultures often personified it as mystical figures or symbolic characters. In Greek stories, Selene is depicted riding across the night sky. In Norse tales, Mani guides the moon through darkness. In China, Chang'e lives on the moon after consuming a magical elixir. Blood moons, eclipses, and unique lunar phases were interpreted as omens, sometimes positive, sometimes foreboding. These stories reflect humanity's fascination with the moon's changing appearance and its mysterious presence in the night sky. Lunar myths show how imagination and observation combine to explain natural phenomena. Even without scientific tools, people recognize that the moon's behavior mattered, inspiring legends and cultural narratives that endure to this day. Fact 79. Cultural significance across civilizations. The moon has held deep cultural significance worldwide. It has guided religious rituals, agricultural practices, navigation, and storytelling. Many ancient temples and monuments are aligned with lunar events, such as full moons or solstices, reflecting the moon's spiritual and practical importance. In some cultures, the moon symbolizes femininity, cycles, and rebirth, while in others, it represents power, mystery, or guidance. Lunar festivals celebrate these themes, connecting people to celestial rhythms and reinforcing cultural identity. By shaping calendars, agriculture, and religious life, the Moon became a central figure in human civilization, a shared thread linking diverse societies across time and space. Fact 80. Moon in art and literature. The Moon has long inspired art and literature. Poets, painters, and writers have used its light, phases, and symbolism to convey emotion, romance, and mystery. From classical poetry celebrating the full moon to modern novels exploring its eerie or fantastical qualities, the Moon remains a powerful creative muse. Artists often depict the Moon as a companion, a symbol of reflection, or a source of wonder. Its changing phases represent time, transformation, and the cycles of life. In literature, the Moon frequently sets moods, guides characters, or underscores themes, making it a universal symbol in storytelling. Through creative expression, the Moon connects science, imagination, and culture. Its presence in art and literature reminds us that this celestial body is more than rocks and dust. It's a source of inspiration, fascination, and human connection across centuries. Fact 81. First moon landing, Apollo 11th, July 20th, 1969, is a date etched in human history. Apollo 11 achieved what generations of dreamers could only imagine: humans landing on the Moon. The mission, commanded by Neil Armstrong, with Michael Collins piloting the command module and Buzz Aldrin as the lunar module pilot, marked the first time humans set foot on another world. The journey wasn't simple. Apollo 11 had to travel nearly 384,000 kilometers through space, with navigation, life support, and communication systems tested to their limits. The lunar module, Eagle, separated from the command module and descended toward the Sea of Tranquility, a flat region chosen for its relative safety. Armstrong and Aldrin carefully maneuvered the module over rocky terrain, dodging boulders and craters before touching down with less than 30 seconds of fuel remaining. Millions around the world watched live as Mission Control confirmed, the Eagle has landed. It was a triumphant moment for NASA, the United States, and humanity as a whole, symbolizing the power of science, determination, and international curiosity. The first moon landing wasn't just a technical achievement, it was a cultural phenomenon. It inspired music, art, literature, and a generation of scientists and engineers. Apollo 11 transformed our understanding of space, proving that humanity could leave Earth and walk on an entirely different celestial body. Fact 82. Neil Armstrong's first step after landing. Neil Armstrong took the historic first step onto the lunar surface, uttering words that would echo through history. That's one small step for man, one giant leap for mankind. The moment was both simple and profound, a human being standing on another world for the first time. Armstrong's careful movements were shaped by the Moon's low gravity, roughly 1/6 of Earth's. Each step had to be deliberate, testing how human muscles and balance responded in a foreign environment. Every motion provided critical data for future missions, from walking and climbing to handling tools and collecting samples. Armstrong planted the American flag, took photographs, and set up scientific experiments. His first step was a symbol of courage, meticulous planning, and the human desire to explore. It showed the world that our species could reach beyond our home planet, creating a bridge between imagination and reality. Fact 83. Buzz Aldrin's contribution. Buzz Aldrin, the second man on the Moon, played a critical role in Apollo 11's success. While Armstrong took the first step, Aldrin followed, documenting the surface, conducting experiments, and collecting rock samples. He also captured iconic photographs, including the now famous image of his own shadow, stretching across the lunar soil with Armstrong in the background. Aldrin's focus on scientific observation ensured that Apollo 11 wasn't just a symbolic mission, it was a real exploration. He helped deploy the seismometer and solar wind experiments, which continue to provide valuable data today. His calm precision under pressure demonstrated the skill required to operate in such an alien environment. Buzz Aldrin's work proved that exploration isn't just about heroics, it's about preparation, teamwork, and the ability to perform science in extreme conditions. Fact 84. Apollo 12 and 14 missions. After Apollo 11, NASA continued lunar exploration with Apollo 12 and 14. Apollo 12 launched in November 1969. focused on precision landing, touching down near the Surveyor 3 probe to test targeting accuracy. The crew retrieved parts from Surveyor and conducted experiments, showing that astronauts could land exactly where planned. Apollo 14 in 1971 overcame early technical difficulties to explore the Fra Mauro region. Alan Shepard famously hit 2 golf balls on the Moon, a light-hearted moment in a serious mission, while the crew collected hundreds of kilograms of rock and soil samples. These missions deepened our understanding of lunar geology, building on Apollo 11's achievements and preparing for longer, more complex missions. Fact 85. Apollo 15, 16, 17, extended missions. The final Apollo missions, 15, 16, and 17, were ambitious and science-focused. Unlike earlier missions, they included the Lunar Roving Vehicle, allowing astronauts to travel greater distances and explore diverse terrain. Apollo 15 explored the Hadley Reel and collected volcanic samples, while Apollo 16 studied the Descartes Highlands. Apollo 17, the last moon mission in 1972, carried geologist Harrison Schmitt, the only scientist to walk on the Moon. The crew conducted extended experiments, gathered extensive samples, and deployed instruments that transmitted data for years. These missions demonstrated how humans could explore, adapt, and study another world in detail, leaving a legacy of knowledge and inspiration for generations. Fact 86. Lunar rovers used in Apollo missions. Apollo missions 15, 16, and 17 brought a new level of mobility to lunar exploration, the Lunar Roving Vehicle or Moon Rover. Before this, astronauts were limited to walking short distances around the landing site, but the rover expanded their reach, allowing them to cover several kilometers in a single excursion. The rover was a lightweight, battery-powered vehicle with 4-wheel drive, designed to handle the Moon's low gravity and rugged terrain. It wasn't just about transportation. Astronauts used it to carry tools, experiments, and rock samples, greatly increasing the scientific return of each mission. They drove across craters, hills, and valleys, visiting sites that would have been impossible to reach on foot. The rover also tested engineering concepts for future extraterrestrial vehicles. Its ability to operate in low gravity, deal with fine lunar dust, and navigate tricky terrain provided invaluable lessons for later robotic and human exploration. Photos of astronauts driving across the lunar surface, kicking up dust clouds in slow motion, captured the imagination of millions and remain some of the most iconic images in space history. Fact 87. Samples brought back to Earth. One of the greatest achievements of the Apollo missions was bringing the Moon back to Earth, literally. Over 6 missions, astronauts collected more than 380 kilograms of lunar rocks, soil, and core samples. These materials have been studied by thousands of scientists, unlocking the Moon's secrets in ways telescopes never could. The samples included basalt from ancient lava flows, anorthosite from the highlands, and delicate soil particles that tell a story of billions of years of impacts, solar wind, and cosmic radiation. Radiometric dating of these rocks confirmed the Moon is about 4.5 billion years old, giving insight into the early solar system. These samples also revealed clues about the Moon's volcanic history, the formation of its crust, and even tiny traces of water. Some of the rocks are so ancient that they predate life on Earth, offering a window into a time we can only imagine. The return of lunar samples remains one of humanity's most tangible achievements in space exploration. Fact 88. Soviet lunar missions. While NASA was landing astronauts, the Soviet Union was making its mark with the lunar program. Beginning in 1959, lunar missions achieved several firsts. The first human-made object to impact the Moon, the first spacecraft to photograph the far side, and the first robotic sample returned to Earth. Lunar missions were uncrewed, but they paved the way for understanding the Moon's surface and conditions. They provided critical reconnaissance for landing sites, tested technology for soft landings, and returned valuable data on lunar soil and radiation. Despite Cold War competition, the lunar missions contributed significantly to global knowledge, complementing human exploration with robotic precision. Fact 89. Modern moon probes. In the 21st century, lunar exploration has experienced a renaissance. Modern probes like India's Chandrayaan-1, China's Chang'e series, and NASA's Lunar Reconnaissance Orbiter continue to map the Moon, search for water ice, and study geology in unprecedented detail. These missions use advanced instruments to detect water, measure surface composition, and photograph terrain at resolutions unthinkable during Apollo. They also test technologies for future landings, sample collection, and even potential lunar bases. Each probe builds on past knowledge, proving that robotic missions remain essential partners to human explorers. Modern probes have also sparked international collaboration. Data is shared globally, allowing scientists everywhere to participate in discoveries that may ultimately support long-term habitation and resource use on the Moon. Fact 90. Artemis Program and Future Plans. NASA's Artemis program marks humanity's return to the Moon with ambitious plans. Scheduled to land astronauts near the lunar South Pole, Artemis aims to explore regions rich in water ice and test technologies for sustainable lunar living. Unlike Apollo, Artemis focuses on long-term presence, building habitats, testing life support systems, and preparing for missions to Mars. The program will include astronauts of diverse backgrounds, robotic assistance, and international collaboration. Lunar Gateway, a small space station orbiting the Moon, will serve as a staging point for exploration. Artemis represents a new era, not just visiting the Moon, but learning to live and work there sustainably. This next chapter of lunar exploration shows how far we've come, from the first footsteps of Apollo to plans for colonies and research hubs. The Moon remains a laboratory, a challenge, and a symbol of human ambition. Fact 91. Lunar geology studies. Studying the Moon's geology is like reading a history book of the solar system. Lunar rocks, soil, and surface features provide clues about its formation, volcanic activity, and the impacts that have shaped it over billions of years. Scientists analyze basalts from lava plains, anorthosite from the highlands, and breccias formed by meteorite collisions to understand its structure and evolution. Even without humans walking on it, orbiters and landers help map the Moon in exquisite detail. By combining surface data with samples brought back by Apollo and lunar missions, researchers reconstruct the Moon's geological timeline. They can see how ancient lava flows filled craters, how the crust cooled from a magma ocean, and where tectonic stresses created rills and ridges. Lunar geology isn't just about curiosity. It informs our understanding of planetary formation, including Earth. The Moon preserves a record of the early solar system, untouched by erosion or atmosphere, making it a pristine laboratory for learning about planetary evolution. Fact 92. Lunar gravity for experiments. The Moon's gravity, about 1/6 of Earth's, offers unique conditions for scientific experiments. It affects everything from human physiology to fluid dynamics, giving researchers insights impossible to obtain on Earth. Astronauts on Apollo missions observed how reduced gravity influenced walking, jumping, and handling tools. Lunar rovers had to be specially designed to navigate low-gravity terrain. Scientists have also used lunar conditions to study plant growth, dust behavior, and material properties. Future missions will leverage lunar gravity for more advanced experiments. It's a natural laboratory for testing technologies for Mars, where gravity is about 1/3 of Earth's, and for understanding how humans might adapt to living in lower gravity environments for extended periods. The Moon's gentle pull is both a challenge and an opportunity for science. Fact 93. Astronomy from the Moon. The Moon could be one of the best places in the solar system to observe the universe. Its lack of atmosphere eliminates distortion and light pollution, offering a clear, stable view of the stars, galaxies, and distant objects. Radio telescopes placed on the far side could operate free from Earth's interference, opening windows into the early universe. Even small observatories could detect faint signals that are otherwise blocked by Earth's atmosphere. The Moon's long nights, lasting about 14 Earth days, provide uninterrupted periods for observation. Future lunar telescopes could revolutionize astronomy, helping answer questions about dark matter, exoplanets, and cosmic origins. Astronomy from the Moon isn't just a dream, it's a practical strategy to push the boundaries of knowledge while preparing infrastructure for human presence in space. Fact 94. Potential lunar bases. Establishing a base on the Moon has long been a goal for space agencies. Lunar bases could serve as research hubs, testbeds for living in low gravity, and staging points for missions to Mars. Locations near the poles, with access to water ice and near constant sunlight, are prime candidates. A base would need habitats to shield astronauts from radiation and micrometeorites, life support systems to provide air and water, and energy solutions like solar panels. Robotics could assist with construction, maintenance, and exploration. A lunar base would not just be a scientific outpost, it would be a symbol of human ambition, demonstrating the ability to live and work sustainably beyond Earth. It's the first step toward humanity becoming an interplanetary species. Fact 95. Mining lunar resources. The Moon holds valuable resources beyond water ice, including metals like iron, titanium and aluminum, as well as helium-3, a potential fuel for future fusion reactors. Mining these materials could support construction, fuel production, and even energy generation on Earth. Robotic mining systems and automated processing could extract resources efficiently, reducing the need to transport everything from Earth. Lunar regolith could be used for building habitats through 3D printing, turning the Moon itself into a construction material supplier. Mining lunar resources is more than economics. It's about enabling sustainable human presence, creating infrastructure, and advancing space technology. The Moon could be the first extraterrestrial frontier where humans learn to live off the land. Fact 96. Solar observation from the Moon. The Moon offers a unique vantage point for observing the Sun. With no atmosphere to scatter light, lunar telescopes can capture solar activity in stunning detail. Solar flares, coronal mass ejections, and sunspots can be studied without atmospheric distortion, providing precise data that helps predict space weather and protect satellites and astronauts. During lunar nights, instruments can be powered down or stored safely, while long daylight periods allow continuous monitoring. Permanent solar observatories could track the Sun's cycles over decades, improving our understanding of its influence on Earth. Observing the Sun from the Moon isn't just science, it's a window into the forces that shape our solar system. Understanding solar activity helps safeguard technology, life on Earth, and future space missions. The Moon's quiet environment makes it a natural laboratory for solar astronomy. Fact 97. Lunar telescopes. Advantages. Telescopes on the Moon offer advantages that Earth-based observatories can't match. Without an atmosphere, there's no blurring or absorption of light. The far side of the Moon is shielded from Earth's radio noise, making it ideal for radio astronomy. Observatories here could detect faint signals from the early universe, and even search for extraterrestrial signals. The long lunar night provides extended observation periods, sometimes lasting 14 Earth days, allowing uninterrupted data collection. Low gravity simplifies launching instruments into stable positions, and the solid surface offers a stable base compared to orbiting telescopes. Lunar telescopes could revolutionize astronomy. From studying distant galaxies to mapping the universe's evolution, they provide a perspective impossible from Earth. The Moon is more than a surface to explore, it's a platform for seeing the cosmos with unprecedented clarity. Fact 98. Long-term colonization challenges. Living on the Moon isn't easy. Radiation from the Sun and cosmic rays, extreme temperature swings, micrometeorites and low gravity all pose serious challenges. Habitats must protect astronauts while providing air, water, food, and waste recycling. Energy systems, such as solar panels, must function during long lunar nights or use energy storage solutions. Psychological and social challenges are equally significant. Isolation, confinement, and the harsh environment require careful planning and support systems. Technology must be robust, redundant, and easy to repair. Despite these obstacles, lunar colonization is within reach. Robotic assistance, advanced life support, and modular habitats are being developed to create sustainable bases. Overcoming these challenges will teach humanity how to live on other planets, preparing us for Mars and beyond. Fact 99. Moon as stepping stone to Mars. The Moon isn't just a destination, it's a launch pad. Its low gravity and proximity make it an ideal staging ground for missions to Mars and other parts of the solar system. Fuel, water, and supplies mined on the Moon could reduce the need to carry everything from Earth. Lunar bases provide a testing ground for technologies needed on Mars: habitats, life support, robotics, and radiation shielding. Astronauts can learn to live in a harsh environment close to home with relatively quick access to Earth for support. By establishing sustainable operations on the Moon, humanity gains experience, infrastructure, and confidence for deeper space exploration. The Moon becomes the first step in a grand journey toward becoming an interplanetary species. Fact 100. The Moon's legacy for humanity. The Moon has shaped human history, imagination, science, and exploration. From guiding calendars and inspiring myths to enabling the first human steps on another world, its influence is profound. Apollo missions proved what humans can achieve, while modern missions and Artemis promise a future of long-term presence. The Moon teaches us about planetary formation, Earth's evolution, and the possibilities of life beyond our planet. It challenges us technologically, socially, and scientifically. It inspires art, literature, and dreams of adventure. Ultimately, the Moon's legacy is about perspective. It reminds us of our place in the universe, our curiosity, and our drive to explore. It's both a mirror reflecting Earth's history and a window into humanity's future, a silent companion guiding us to